The previous lecture's code successfully computed the sum of the first n natural numbers. However, a working solution doesn't always mean that we found the optimal way to solve a particular problem. Our test revealed that our function's performance deteriorates as the input gets bigger. Carl Friedrich Gauss is said to have found a better way to calculate some n in his early youth. In the late 1700s, Gauss was only an elementary student. He amazed his teacher with how quickly he found the sum of the integers from 1 to 100 to be 5050. Gauss recognized he had 50 pairs of numbers when he added the first and the last number in the series, the second and the second last number in the series, and so on. That can be expressed using the following formula, known as the triangle numbers formula. Sum n equals n times n plus 1 divided by 2. Gauss was probably not the first to discover this formula. Likely, its origin goes back to the Pythagoreans, and it was known as early as the 6th century before Christ. Alright, given this formula, we can implement an improved version of the sum function. I create a new function and call it sum optimized. It takes the argument n of type int and returns an integer just like its sibling. Now, instead of applying a for in loop, I'm going to apply the triangle numbers formula. So we return n times n plus 1 divided by 2. The sum optimized function is not only shorter, but its execution time doesn't depend on the input size. Let's run the same tests as we did for the sum function. I'm going to copy the for in loop and paste it here. And we call the sum optimized function in this case. Let's print what we're doing. I print a message for the sum optimized part in a new line and also for our original measurement here. And let's also change the f string in the second case. Now let's run our program, and here are the numbers. The results show that the execution times for the sum optimized function do not vary regardless of the input size. There are only some minor negligible differences in the range of microseconds. Besides, sum optimized is more efficient even for smaller values. Sum optimized, unlike the sum function, doesn't depend on the input size. By applying a smart 2000-year-old formula, we managed to implement a solution with optimal performance. Hope you've got a taste of what algorithms can do for your code's elegance and speed. Finding the optimal approach requires more analysis for sure, but the results are definitely paying off.